Okay, physics, welcome back. I want to talk you through the derivation of the electrical field for a that exists inside of a spherical object. So two cases. One case, we're going to have a conductor. It's a trivial case, and a conductor, remember, my charges are going to move away from each other. So if I put a positive charge on my conductor, it'll move away, and those charges will be found on the very outside surface of whatever object I have, in this case a sphere. So if I go inside that, any point inside here, whatever charge I put there is going to experience a force in equal magnitude in opposite directions, so it's going to cancel out. So there's no net force that's going to be experienced, and that means there's no net electrical field that's going to be present there. So inside a conductor, whatever the charge is on the outside, what matters is my enclosed charge, and there's no enclosed charge, so there's going to be no electrical field. So the problem comes when I have let me draw a bigger one. When I have a non-conductor, so I have an insulator, so something where the charges stay put. And I'm going to make a couple of assumptions, or usually they tell me that I'm going to have a uniform charge density, and we're going to use that. So in this case, what am I looking for? So I have some point here. It's my center, so I'm going to have some point here that I'm interested in. I want to find the electrical field at that point inside the conductor. So here's the challenge, though. So remember that stuff that's on the outside cancels out. So all the stuff that's in here, right, on the outside of this donut, and all that charge is going to be pulling equally in opposite directions. It's going to cancel out. So that doesn't contribute to an electrical field. All that matters is that enclosed charge. And again, we'll use Gauss's law to try to figure this out. But importantly, as I go inside, then there's less charge that's causing my electrical field. I'm closer to it, I'm closer to the center, but there's less of it, so it's not going to be a simple thing. So let's figure out. Remember, Gauss's law tells me, well, I'm working with flux, so I have two ways of calculating flux. One is E dot A. So I take the dot product of my two vectors, and I can get the total amount of flux that's there. So what I'll try to do is combine that with Gauss's law, which says the total amount of flux is going to be equal to the charge that's enclosed divided by some constant, epsilon naught. So what we want to do is we want to set this equal to, I have two things I'm trying to set up my Gaussian surface. So E is constant everywhere, so E is going to be the same everywhere on this surface, and I need to figure out what is the magnitude of this two-dimensional surface. So what is the area? Area for a sphere, surface area of a sphere is 4 pi r squared. Notice I'm using lowercase r to indicate my distance to my Gaussian surface. That's good. So I'm looking for electrical field. I have the area, so I need to figure out Q enclosed, and then I can have enough things so I can set these equal to and solve for that. So the charge is the tricky one. So here I'm going to use volume density, which is going to be the charge divided by the volume. And it's going to be my total charge by my total volume. So let me set my total distance here as being capital R. And what I'll say is that total charge divided by my total volume is also going to be the same ratio when I have my small amount of charge divided by my small amount of volume. So I'm going to look up the volume of a sphere. I'll discover volume of a sphere is going to be 4/3 pi r cubed. I'm going to be careful about which r I'm using here. So I'm going to have my total charge divided by the volume of my total sphere, so which is going to be 4/3 pi capital R cubed. And this is going to be equal to the charge that's enclosed, so I need to find that, divided by the volume inside here. So this is a three-dimensional volume that we're worried about here, so this is going to be 4/3 pi lowercase r cubed. Some things cancel, but notice r's do not cancel, right? So this is the distance to the outside of my whole object, and this is the distance to the Gaussian surface that I'm interested in. So the 4/3 pi is going to cancel. I can get Q enclosed as being a ratio of my cubed distances times the charge. Okay, so now I have enough. So I can plug this in. I can say, well, I'll set up the integral form of this. So my closed surface integral of my electrical field times the area of this is going to be equal to Q enclosed over epsilon naught. I know E is going to be constant, so I'm going to pull that out. Q enclosed, I have a value for this, which is r cubed over capital R cubed times Q times 1 over epsilon naught. Keep my constant there. And I know that this, when I evaluate this, right, I'm going to take a closed surface integral of dA, which is going to be my total area of that surface of that sphere, which is 4 pi r squared. So E times 4 pi r squared. And usually our integrations for Gauss's law are pretty simple. You want to get the surface area of whatever the object is that you're looking at. So, and then I have my ratios here times Q, and I put epsilon naught on the bottom. And now I try to make some sense out of this, right? So what's going to happen, I'm going to have, so these lowercase r squared will take away 2 of those, and I'll rearrange this to get an equation for my electrical field, which is going to be Q times R divided by 4 pi epsilon naught times capital R cubed. Right? So think about, how does this change? Well, remember, capital R is a constant, Q is a constant, epsilon naught is a constant. The only thing that's changing here is R. So if I plot what this looks like inside, so as my electrical field goes from 0 to R, what does this look like? Well, it's going to be linear. Right? As R increases, as my radius increases up to the outside of my sphere, outside my sphere, then something different happens, right? Now I'm outside my sphere, and that's going to decrease what is it, with the square of the distance from them. I'm going to have something that drops off. So I'll get a graph that looks like this. Anyway, hope that helps, and we'll talk to you soon. Bye.